Good morning, students.
Good morning, sir.
How are you guys doing today?
Yeah, good, sir.
Oh, good, Ben. And I believe you are doing well. You are the only one who responded. So I believe
Yeah,
you
we
are
are all
doing
doing well. We are all doing well, sir.
well. Engineer, are you sure you are doing well? So why didn't you respond? Yesterday, I didn't see you for the environmental class.
Hmm.
You and Kingsley, you guys are on a shift. The day you will come, where is Kingsley? Is Kingsley there?
Yeah,
Kingsley.
Yes, sir. Please, I'm here.
Okay. So today, you all reported to duty.
yesterday I was having some running stomach. It's not easy for me, so I went there. I was I went there buy space at the washroom and and I was there the whole day yesterday.
But engineer, you could have been
Yeah.
in your room, closer to your washroom, and then you'd be listening.
So I will not feel comfortable.
Oh, come on. All you
Then,
need to do is just mute yourself quickly. You can even sit on the thing and still be
it,
listening.
it is not. It is
Engineer,
not
stop
just a
lying.
running. I'm feeling some abnormal, some slight
Engineer, stop
pain.
lying. Stop. Stop. Stop.
Engineer is trying to justify himself.
Don't mind him. Don't mind him. If you had told me that you had malaria or you are coughing, crowd there is different. But that thing, you can even sit on the bowl and then be listening.
Every really.
You bring all your accoutrements, all your laptop, everything in the room, and then you be there. Anyway, today we are going to do chemical reactions and equations. All right. So let's set the ball rolling and then and study for today. All right. So chemical reaction. So chemistry is largely about chemical changes. That's what chemistry is all about. Chemical changes. What chemical will change from one form to another. You get it? If there's no any chemical change, then there's no chemistry. Then there will be no chemistry. So it's all about having some kind of species, and you change it from one form to another. Then that's chemistry. So chemical changes is part of the fundamentals of chemistry. All right, that's fundamental. For example, if you have hydrogen and you add it to oxygen, you get water. Now we've known the reason why we have two uh, atoms of hydrogen and then two atoms of oxygen that can give you two. I mean, that can give you water. We know based on the bonding. You saw it. We did those kind of bonding, the octet rule and stuff like that. So you say, oh, okay, if I have this amount of hydrogen, then I know this amount of oxygen, and when I put it together, I can get water. All right. So we did that. All right. So like how you see here, right? That that equation is not balanced. Who can tell me the reason why it's not balanced? Who can tell me the reason why it's not balanced?
Because the, there are two. So is it the H2O, the water?
Yeah, the hydrogen molecule and then the oxygen molecule give us H2O, give us water, right? So why is it that it's not balanced?
Sir,
Yeah, who can help?
sir, please, on the left hand side, the oxygen atoms are two, and on the right hand side, the oxygen atoms are only one,
Very
which
good.
makes it.
Well done. Well done. See? Yes. So that's why it's not balanced. The reactant, have two atoms of hydrogen and then 2 atoms of oxygen. But when you come to the product side, you have 2 atoms of hydrogen and just only 1 atom of oxygen. So that means it's not balanced. All right. In the course of this lecture, we will see how we balance the equations, see how to balance the equation. And that helps us to know a whole lot of stuff, to be able to know that, oh, okay, if I have, hydrogen, this amount of hydrogen, and I have this amount of oxygen, I can have this amount of water. If I have this amount of water, and then I have this amount of, I know I have to have this amount of oxygen and this amount of hydrogen to give me the amount of water. So we do that. So it's not balanced, like how your classmate said, because the atoms are not the same on both sides. All right. So this is an example of chemical equation, the one we just saw, which is a concise way of representing a chemical reaction. The initial substances are called reactants, and the final substances are called the products. So in chemical equations, the number of atoms of each element in the reactants must be the same as the number of atoms of each element in the product. Again, in chemical equations, the number of atoms of each element in the reactants must be the same as the number of atoms of each element in the products. When the reactants and products of a chemical equation have the same number of atoms of all elements present, it is said that an equation is balanced. An equation is balanced. All right.
Yeah.
Yes.
Yeah,
Philip.
sir. Because of the equation you put earlier, I wanted to ask some question then.
Go
So that
ahead.
so in our CO2 plant, we when we produce the CO2, the end product, we have another chamber that we introduce water to wash the CO2 for any impurities.
Yeah.
Now, in that process, because we don't want because water is hydrogen and oxygen, we introduce CO2 into the water that we use to wash the CO2, so that it will flash the the
The CO2.
yeah, the CO2. So is in that process, is it removing all the hydrogen atom and the oxygen atom, or what? Because water is hydrogen and oxygen. So if we are
Yeah.
introducing CO2 into the water, so that we will not have any other gases being, touching to the CO2, are we removing all the hydrogen atom and the oxygen atom?
Not really removing, because they will react, right?
Okay. Okay.
They will react. So the CO2 bond with the hydrogen, right, to
Okay.
give you bicarbonate.
Okay.
Yeah, to give you bicarbonate. All right.
Okay.
So you are not, matter of fact, they are just moving it somewhere, but it's just kind of reaction that you guys are forming.
Mm.
And all these things too, it depends on the conditions, meaning
Okay.
the temperature and pressure that
Mm.
is involved with those kind of, because there are some reactions that you need to give it a specific temperature and specific pressure, to be able to get what you're looking for.
I see.
Engineer, you see how it goes.
Yes, sir.
So it's not really essential, like, but that removing maybe all the hydrogen atoms or oxygen atoms, but it's a reaction that they want to get something out of it. Yeah, that's why they're introducing water to it. Do you understand what I mean?
Mm.
Do you get it, engineer?
Yes, sir.
Okay. So now, in the initial substances, like I said, they are reactants, and then the final substances are called the products, right? And then the number of atoms in the reactants must be equal to the number of atoms of that particular species in the product. So when they are the same, both reactant side and the product side, we say is balanced. The equation is balanced. Okay. So there are some steps we need to follow to really do the to balance the equation, right? To balance the chemical equation. And this is the steps. You count and list the number of each type of atom on each side of the arrow, which is the product side and then the reactant side. Then you look for elements that occur once on both sides of the equation. The one that happen to be on one side of the equation. Then you change the coefficient, right? You change the coefficient so that these elements are balanced, right? Those that occur on only one side of the equation. So when you change it, it will balance it if necessary, right? Then change the coefficient of any remaining components to accommodate the changes made in step 3, right? Then you check the balance equation to be sure that the number of each atom are equal on both sides of the equation. All right. So these are the steps that you go through one by one to make sure that you get what you want. All right, to balance the equation. So chemical equations, right? Why are we balancing the chemical equation? We are so serious about balancing this. It tells about the relative number of reactants and products involved in the reaction. All right. It says the relative number of the reactants and products involved in the reaction. The molar masses of the reactants and products link the number of reactants and products with their masses. Again, the molar masses of the reactants and products, they link the number of reactants and products with their masses. All right. So the balanced equation can be used to determine how many grams of one of the substances will be needed to react with a given mass of another. How many grams of products can be produced by the reaction or a specific mass of a reactant. All right. So this is what we call the stoichiometry. Stoichiometry is the quantitative relationship, right, between elements and compounds in chemical reaction. Stoichiometry is a quantitative relationship between elements and compounds in chemical reactions. Then we have this called mole ratios. Mole ratios are conversion factors that relate the number of reactants consumed to each other or to the number of products molecules formed. All right. So we use the stoichiometry, we balance it, and then we balance it, and then we see that okay, this is how much amount of this reactant that I need to give me this amount of the product. This amount of product that I have, okay. Then if I have this amount of product, then how much of the reactant do I need to give me the product that I'm looking for? Right. So let's use it as an example. We have aluminum. Right? We have this iron 3 oxide. We have this then they bond to give us aluminum trioxide. Then we have iron. All right. Here you see the stoichiometry, you see the mole relationship. These 2 moles of aluminum, this is 1 mole, this is another 1 mole, and this is the 2 moles. All right. So then here we have 53.96 grams. Here we have 159.7 grams. And then this is 101.96 grams. And we have 11.70 grams. All right. So that one tells us that, okay, if I have, This 53.96 grams are bonded with, of aluminum, and are bonded with iron 3 oxide with 159.7 grams. I'll get 101.96 grams of aluminum trioxide, and then I'll get also iron 111.7 grams. All right. So that is the relationship that's, balancing the equation helps us to really, do our work in chemical reactions. All right. That's what it helps us in our chemical reaction. All right. So any questions so far? Any questions so far? All right. So if there's no any question, then we can just we can move on to do, other stuff. So the question here is this: how many molecules? How many molecules are needed? How many molecules of sulfur trioxide are needed to I needed to react with 144 molecules of iron 3 oxide, giving this balanced chemical equation, right? So first of all, we try to see whether this is really indeed balanced, right? Here we have two atoms of oxygen. Okay, you guys should tell me whether it's balanced or not. Tell me whether it's balanced or not. And if it's balanced, why is it balanced? Let's check. Let's check to see, all right, whether it's balanced. And if it's balanced, tell me why is it balanced. Everybody get to work. I'll give you some few minutes, maybe 2 or 3 minutes, to check for me. All right, so who can tell us whether it's balanced or not?
Sir,
Yeah, go ahead, Ernest.
please, the question is balanced from my view.
Okay,
So
tell
if
us
I'm
why.
doing the elements one by one, the Fe is 2 on the left hand side and 2 on the right hand side with a
Good.
subscript. And with the O is 3 on the left hand side plus 9 on the left hand side, so making 12. And with the right hand side, it is 4 times 3. making 12 on the right hand side. So that one is balanced. And with S is 3 times 3 on the left hand side, that's 9. And on the right hand side, no, it's 3 on the left hand side, and the right is 3. Sorry, making that one to balance.
Well done, Ernest. Well done. Thank you so much. Is there anybody has different kind of view about what Ernest said? Yeah, Ernest, you are right. Well done. Well done. So it's balanced. So we first have to balance it first before we use it to do any. If you don't balance it, all right, and you use it to do work, you get them wrongly. Yeah, you have an answer though, but your answer will be wrong. So that's why we spend time to learn how to do the balancing. All right. So Ernest is definitely right. All right. So now the question is, let's go ahead and solve the question. All right. We have 144 molecules of iron 3 oxide and now sulfur trioxide. We needed how much to give us like that for the also molecules, right? So we use this relationship that 144 molecules of iron 3 oxide. Then we use the mole to mole ratio, right? The mole to the coefficient. Right here, we have 3 molecules of sulfur trioxide and one molecule of iron 3 oxide. All right. So we come here, we use this one here. It's 1 here. We don't write it. It's like writing X. When it's 1X, we don't write it. So this is one of them here. And then this is 3. All right. The coefficient is 3. And here the coefficient here is 1. So we use that relationship. And then it says 3 molecules for sulfur trioxide, and 1 molecule is iron 3 oxide. Then we multiply by 144 molecules of iron 3 oxide. And then this iron 3 oxide molecule will cancel iron 3 oxide molecule, leaving the molecules of sulfur trioxide. The only when you do the multiplication and division, you come up with 432 molecules of iron sulfur trioxide. All right, so that's how you tackle second problem. But first of all, you have to make sure that you balance your equation. All right. So now, to balance the equation for the first one that we just saw, right, for the water like this, all right, Ernest told us that it wasn't balanced, right? Do this one element at a time, right? Going from one side of the reaction to the other side, changing the number of molecules of a substance until all elements have the same number of atoms on each side, right? So we're stressing on this balancing thing, all because if you don't get that one straight, all your work that you do eventually will not really, be well for you. So you have to let's try as much as possible to learn how to balance your equation. All right. Maybe there may be other method that some people use to balance the equation, but I'm going to show you, this method. And if you have any other method that seems very good for you, that can help you, fine. But make sure that you learn it very well. But this one, it works. And the one I'm showing you works. Why am I saying is because I see that, so I see some of my students sometimes they'll present different methods, to balance the equation. All right. Maybe some of them went to high school, doing chemistry. When they went to high school, they did chemistry. And so in the end, they present it, and then some of them get it right. Some of them too, they get it wrong. But this method too, whenever they do it, they get it right. So, and I recommend this method too. All right. This is like going from campus to Kaneshi. You can pass through Circle, or you can come and pass through La Paz and go through some other place and go to Kaneshi. And so, but you find the best route where you not get accident, where the traffic will not catch you, and where people will not worry you. Maybe the police may be at the corner, trying to make sure that you're wearing your seatbelt, which when you wear it will be good for you. So it's the best way to do things that you are looking for. All right. So now this water here, like how Ernest told us in the beginning, that it's not balanced, and it's true, it wasn't balanced. All right. So then, how do you balance it? You take a hydrogen appears one side here, and also appear 1 here. All right. So this is and then oxygen 2 appears 1 here and 1 here. So it doesn't matter which one we start to balance first. So we choose the oxygen, right? Here oxygen is 2. Oxygen was 1. And so we multiply and here by 2. All right. So when we multiply here by 2, we have oxygen 2 though. Oxygen will be 2 here. Hydrogen will be 4. All right. But hydrogen is 2 here, on the left side. All right. On the reactant side. So then what do? You just have to multiply the reactant, which is the hydrogen, by 2. So when we multiply by 2, then we get 4 hydrogen on the reactant side. And then when we come to the right side, which is the product side, we'll get 4 hydrogen here, and then 2 oxygen, and then 2 oxygen on the reactant side. So then we count them one by one. Make sure you count them one by one, and then making sure that all the elements on one side are equal to the elements on the other side, and then we'll balance it. All right. So that's how we tackle it. All right. This one is simplified, a simple form, right? A simple one. All right. So let's write the balanced chemical equation for each of the given chemical reaction. Right. Everybody get to work, and let's see how you balance it. All right, and come up with let's see the solution is there though. So on your where you have paper, try to do it yourself, and let's see how you balance it. All right. How about you get to work? Get to work. I'm giving you some minutes to do the work, and let's see how you tackle it. All right. So now, who has finished the first one? Who has finished the first one?
So me. I
Okay,
finished it.
engineer.
Yeah.
Engineer, what did you get?
So hydrochloric acid, we have the hydrogen two and then the chloride two atoms. So, but if you see the one, what's in the question is not balanced. So you have to place two in front of the reactants so that it will then it will balance.
So you have the hydrogen and then chlorine, right?
Yeah, chlorine, yes.
So the H will be how much?
The H is two, and
And
then
then the chlorine.
the chlorine two is having two atoms.
Mhm. Okay. So then the HCl, right, will be how much? How many atoms of the HCl will you get for? Hydrogen of the HCl will you get?
Yeah, please come again.
How many atoms of hydrogen in the
Okay, so
HCl will you?
so
Engineer,
say
did you understand my question? So
say
hydrogen H.
two.
Oh, okay. All right. You mean it's going to be like this? Is that what you
Yes,
mean?
yeah.
Yeah, so
Yeah,
this
so this
H.
one, the hydrogen is having two atoms, and this one, the chlorine is having two atoms. So
Okay.
to balance the reaction side, we have
Mm,
to place the two in front of all of them to make it so that
okay.
they
To me.
so yeah, so they share the two.
Oh, okay. Okay. Well done. Well done, engineer. If you are done it this way, then your answer is correct. If you haven't done it this way, you are learning. You are in the learning mode. So you find yourself and ask yourself, well, why didn't I get it right? Then next time, you do, and then you try to balance it. Okay. Yeah. So the other one, all right, let's do it together. Write a chemical equation in terms of the substances involved, right? So ethane plus oxygen gives carbon dioxide and water, right? This is a combustion reaction, all right? This is combustion reaction. Sorry guys, so we are doing together. So ethane plus oxygen give you carbon dioxide plus water. This is combustion reaction. Ethane, so hydrocarbon, and then you add it to oxygen, which is air, right? And now we get carbon dioxide and water. All right. This is it's not balanced, right? It's not balanced. So then, because why is it not balanced? We have two atoms on the for the carbon. We have two, and then we have carbon also only one on the product. Hydrogen, we have just two on the right side. This is the product. All right. Carbon is not balanced. Hydrogen is not balanced. Oxygen too is not balanced. So this one is essentially all of them are not balanced. Right? All of them are not balanced. So we need to see. See two carbon atoms on the left side, which is the reactant side. So two carbon atoms is needed on the product side, right? So you can multiply the carbon dioxide by 2 so that we can get 2 atoms of carbon on the right side. So now the carbons are balanced now. Now I see we have 6 hydrogen atoms on the reactant side. So 6 hydrogen atoms are also needed on the product side. All right. So you multiply the water by 3. You multiply the water by 3 so that we can get 3 atoms um, of hydrogen on the right side. So multiply the water by 3, right? By 3. All right. So now we see that things are not really going the way it has to go because now if you multiply the water by 3, you have 6 atoms of hydrogen on the right side and 6 atoms on the hydrogen on the left side. But then the oxygen will be changing, right? The carbon will be also okay, but the oxygen is different. Now let's see, we have 3 atoms of oxygen on the right side here from the water, and then we have also 4. That will make it what 3 and then 4, which is 7. All right, and then but on the left side we have just only 2 of them. So then we need to manipulate. Go ahead. So now there are 7 oxygen atoms in the product, 4 atoms from the carbon dioxide, and 3 from the water. That means 7 oxygen atoms are needed in the reactants. And oxygen is a diatomic molecule. An even number of oxygen atoms can be obtained at a time. So they can be achieved by multiplying the other coefficients by 2. So you can multiply all other coefficients by 2 so that there will not be, 7. It could be other number, even number. Okay, because oxygen is diatom. All right, it's a diatomic molecule. So then you do that. When you multiply all by 2, then you'll have, had oxygen over on the right side will be how many? This one will be 6, and for the water, and then oxygen here will be 8. So 6 plus 8 will be 14. But then we have here oxygen is only 2. So if you multiply by 7 here, we can get 14 also on the left side. Then that's it. Yeah, balance it. So that's what we do over here, and then we multiply it by 7, right? So once you have done it this way, you don't just close your eyes and say, "Oh, I'm done." No, no, no. You need to take them one by one. See the species. Take them one by one. Carbon. See how many of them are on the left side. We have 4 on the left side and then 4 on the other side. Go with hydrogen. 6, 6 times 2, which is 12. So 12 on the left side and come to the right side, the product side, which is 6 times 2, which is also 12. When I say 6 times 2 times, it comes to 12, right? Some of you know, or some of you may not know, but this is the 2, the subscript. and that is what we use to multiply by the 6 to give us the 12. All right. Here, when we say oxygen here in the water here is on the carbon dioxide is here is how many? 8 is there this 4, right? The coefficient 4 here is what we use to multiply by the subscript 2 here to give us 8. You get it? So here when we say oxygen is 7 with the oxygen down here, that means it's this 7 here that we use to multiply by this 2 here to give us the 14. Yes. So that's how we do it. And this 2 is used to multiply by the coefficient of the carbon and the coefficient of also the hydrogen. Okay, so that's why. So when you count them all, you will realize that, if you have done them correctly, you see that, the number of products, the elements of the product is same to the number of elements of the reactants, then you are done. Okay, if not, then you go back and double and check it. All right. So now we have the type of chemical reaction. We have single replacement and then double replacement. Single replacement reaction and double replacement reaction. All right. So the single replacement reaction is a chemical reaction in which one element is substituted for another element in a compound, generating a new element and a new compound as products. All right. For example, we have HCl, right? HCl, which is aqueous, all right, and then zinc, which is sulfur. I mean, a solid, and then we have zinc, chloride, and then we have hydrogen. All right, the aqueous means they dissolve in a water solution, and then the zinc is not soluble, right? It's not soluble, so that's how it is. All right, so the hydrogen atoms in the HCl are replaced by the zinc atoms. All right, a new element hydrogen is formed. All right, a new element hydrogen is formed. All right, so that is a single replacement. Why? It's only one atom that is replacing, or one element that is replacing the other one. One element is replacing one. Right. For the double, is two of them interchanging. Right. So it's only one here. And now for the one that is replacing, right? When you look on the periodic table or the activity series, see that one has to be on the top and one is down. The one at the top can replace the one at the bottom, but one at the bottom cannot replace the one at the top. So that's how you see it. All right. So let's do example 2 and see how it's applied. We have sodium chloride and iron, give us sodium fluoride and then chlorine gas. All right. So this is the thing. This one, once you break the sodium and chlorine, right, it will have sodium ion and chlorine ion. Now the fluorine, right? The fluorine is going to bond, because this is an ion, right? It will bond with this cation, all right? And then it will, because it's positive and negative, so the positive and negatives will come together and they will form sodium fluoride. And then the chlorine, which is also negative, will stay by itself. But this is the thing. On activity series, right? The one that replaces the other one has to be on the top, all right? And the one has to be on the bottom. All right. Here, remember that the fluorine, right, went ahead and replaced the chlorine. So that you see that the fluorine is on the top of the activity series, and then the chlorine is down on the activity. So that's why he was able to replace it. All right. Chlorine is back at the bottom of it's below the fluorine on the activity series. So you can replace it. But if chlorine happened to be on the top of fluorine, it wouldn't have been able to replace it. Like fluorine wouldn't have been able to replace it. But fluorine is on top of chlorine on the activity series. All right, so then it can replace it. All right. So the negatively charged ion changes from chloride to fluoride. A typical characteristic of a single characteristic of a single replacement reaction is that there is one element as a reactant and another element as a product. Not all proposed single replacement reactions will occur between two given um, reactants, right? Not all. Like I said, that's the reason why. Let's see this example. Will a single replacement reaction occur? Single replacement reaction occur. Is to identify the product. So you have magnesium chloride and iodine, right? And calcium bromide and fluorine. Now let's see where the reaction occur. All right. When magnesium breaks to magnesium ion and chlorine ion, all right? And then we have the iodine, right? Would it be able to replace the chlorine? Would the iodine be able to replace the chlorine? And we have calcium, and then they break, calcium breaks, and then bromine also breaks. And the calcium is positive ion, bromine is a negative ion. And now, will it be able to, will the fluorine be able to replace bromine and then form calcium fluoride? Let's find out. All right. So now, because iodine is below chlorine, iodine is below chlorine on the periodic table, a single replacement reaction would not occur. Because iodine is below chlorine on the periodic table, a single replacement reaction will not occur. All right. Because for the second one, right, because fluorine is above bromine on the periodic table, a single replacement reaction will occur. Right, because it's above it. Fluorine is above it on the periodic table. A single replacement reaction will occur. And the product will be calcium fluoride, right? Because the fluorine has replaced the bromine. Because it's on the top and then bromine is on the bottom. So it has come to replace it. Or this is the activity series. When you have a work, you just have to go and look at it and see that, okay, it's a prediction. We're going to predict that this kind of reaction can occur, single replacement reaction can occur. This activity is for cation replacement and single replacement reaction. Lithium is on the top of potassium, it's on top of barium, strontium, calcium, sodium, magnesium, aluminum. So then the one on the top can replace the one on the below it. Barium can replace strontium, calcium can replace sodium, strontium can replace calcium. So that's how it is. So that's a second. All right, so that's the single replacement reaction. So an element on top will replace an element below it. in compounds undergoing a single replacement reaction. Elements will not replace elements above them in the compounds, right? The one below them, they can't go up there to replace someone. So use the activity series to predict the products, if any, of each of the following equation. All right. So iron 2 chloride and then plus zinc and nitric acid plus gold. All right. So now let's see how the work will be done. Because zinc is above iron in the activity series, it replaces in a compound. The products of this single replacement reaction are zinc chloride and iron, right? Because it's on the top of it, you can replace it. Gold is below hydrogen in the activity series. As such, it will not replace hydrogen in the compound with a nitrate ion. So no reaction can be predicted. All right, no reaction can be predicted. So now we're done with the single replacement reaction. So the double replacement, right, is why we are on it running. Double replacement reaction occurs when parts of two ionic compounds are exchanged, making two new compounds. Right? When parts of two ionic compounds, you have this ionic compound, and then they break, all right? And another ionic compound, they also break. And then when they swap, right? This one will go to this side, the other one will go to the other side. Then you have a double replacement reaction. All right. It's a characteristic of a double replacement reaction is that there are two compounds as reactants and two different compounds as products. All right. Two equivalent ways of considering a double replacement equation. Either the cations are swapped or the anions are swapped. You swap the cations or you swap the anions, and then that will form the double replacement reaction. Here, copper 2 chloride equals plus silver nitrate equals, right? The copper chloride, right? It will break. This will break. Cu will break, and then chlorine, because the ionic compounds. Chlorine will also break, right? And to give you a C plus, Cl plus, and Cu2 plus. I mean Cl minus and Cu2 plus. All right. Cl minus. So this anion, this is cation. And silver to the same thing. All right. Silver will break positive, and nitrate negative, right? So now we have it like this. So then they swapped, all right? The chlorine will go to where the silver, where the nitrate is, to bond with the silver. And then there's nitrate will also go and bond with the copper. All right. So that's how it is. So they swap, all right? Cl will swap with the NO3, right? That's all it's about. And this is a double replacement reaction. Predict the product of this double example. Predict the product of this double replacement equation, right? Barium chloride, sodium sulfate, all right? You break them, break this. Ba 2 plus Cl minus Na plus and then SO2 SO4 2 minus, all right? So now the product will be the swap, the Cl and SO4, Cl2 SO4 will swap, all right? So you have BaSO, no, you have BaSO4, and you have 2 NaCl, all right? Any question here before we move on? So if not, then let's talk about precipitation reaction. Precipitation reaction. A precipitation reaction occurs when two ionic compounds are dissolved in water and form a new ionic compound that does not dissolve. You have this ionic compound, and then we have the other ionic compound. They dissolve. This one dissolves, that one dissolves. And then they form another ionic compound. And those ones, some of them don't dissolve. Right? That's when precipitation occurs. Ionic compound, ionic compound. All right. This guy dissolves, this guy dissolves. And then they bond together. When they bond together, they form another ionic compound. But then that one that they will form, it doesn't dissolve. Because if it dissolves, then we won't have any precipitate. All right. Or it has dissolved. We won't get it out. All right. So if it doesn't dissolve, that means it's forced out of the solution. We can take it, we can sieve it. You can find a sieve it out, or you can use something to take it out. All right. So the formation of a solid precipitate is the driving force that makes the reaction proceed. We have rules that govern it. So we call it solubility rules. Solubility rules are general statements that predict which ionic compound dissolve and which do not dissolve. You say they are soluble. When they dissolve, we can say they are soluble. And when they don't dissolve, we say they are insoluble. Right? If the ionic compound dissolves, we say, oh, this compound is soluble. If it doesn't dissolve, we say, oh, it's insoluble. Okay. If a compound is soluble, we use the AQ label. It's soluble, so we say AQ label, indicating it dissolves. If the compound is not soluble, we use the S. Right? That means it is not soluble. So sometimes it's get a bit confusing. You may think, oh, when it's soluble, then you can use the S because S soluble, SS. No. It's the other way around. When it's not soluble, that's why we use the S when it's, and assume that it will precipitate out of solution. Right? If everything is soluble, then no reaction, no precipitation reaction will be expected because everything will dissolve back. You form the product, and everything has dissolved back to reactants. Right, so that one, it is not soluble. It is soluble. All right. So we have a solubility rule. We have a solubility rule. All right. So this is a table that you need to learn. All right. Solubility rule. So all compounds that generally dissolve in water are soluble. All right. So this compound that dissolve in water, some like lithium, sodium, potassium, rubidium, cesium, ammonia. These compounds, they dissolve in water. And there's no exception. Once you form a compound with these ones, lithium, sodium, potassium, and so forth, these ones, they will dissolve in water. There's no exception. Also, you have nitrates and acetate, all right? This one too, they will dissolve in the water. These ionic compounds. Right? If you have this ion, they form with an ionic compound, they dissolve in water. All right? No exception. No exception. They all dissolve in water. But these compounds, chlorine, bromine, iodine, all right, when they bond with other ionic compounds, right, or different ions, and then they form a compound, they will dissolve in water. But when they bond with silver, mercury, lead, they will not dissolve in water. All right. If this compound, they bond with these three of them, that one, they will not dissolve water. But if they bond with any other ion, they will dissolve in water. So this is the only exception whereby they will not dissolve water. Same thing with the sulfate, right? If they bond with any other ion, they will dissolve in water, except when they bond with mercury, lead, strontium, barium, then they will not dissolve in water. All right. When they bond with this 1, 2, 3, 4, they will not dissolve in water. Now let's see again. This compound generally do not dissolve in water, and they are so insoluble. All right. Compounds of, like for example, carbon trioxide ion, all right, and phosphate ion. For these ones, right, when they're bond with any other ions, they will not dissolve in water. All right, they will not dissolve in water. But when they bond with this, then they'll dissolve in water. Lithium, sodium, potassium, and these ones, ammonium, rubidium, cesium. For these ones, when these carbon trioxide ion and then phosphate ion, then they will not dissolve in water, except with this one. And then the OH hydroxide ion, when they're bond with this, all right, they will dissolve in water. Or if they're bond with any other species, they will not dissolve in water. I think I'll end here. All right, this is Saturday. I'll end here. I'll make you guys go and then just spend your weekend. Okay, and then we'll meet next week. Next week Friday. Okay. So if you have any question, there's some work on this thing that you need to do in the module book that you need to do concerning this, and then read also the module book. I'll post this one also on our platform so that you can go over there. All right. So if you have any question, you can ask me. If you don't have any other question, we can close for today. All right. So that we can also spend our weekend. Yara, is Yara here today? I'm always asking about Yara because she's the only.
Is Yaira.
Yaira.
Yes. But
Oh,
it's simple, you can say blessing. That's the meaning.
oh, it's blessing. Oh, okay.
Yeah.
Which language is that?
Aigbe. Ewe.
She's an Ewe.
Yeah, ewe.
Oh, I see. I thought she was an enough now.
Mm.
Oh, I see. Is Yara there? Okay, Yara or blessing. I see. But Sadat, you're enough now, right?
Sadat.
Uh, Sadat is enough. For Sadat, they are no Sadat. It's enough.
Sir, please, I'm here.
Sadat, you enough now, right?
I'm half a Northern and half a Cool.
So how come you are Sadat?
My father is a Northerner, and my mother is from Cool.
Yeah, but if okay, your father is enough and your mother is a oh, I
Yeah,
see. So that's why okay. So fathers, we name the children. Okay.
exactly.
Oh, okay, now I understand. Which town do you come from?
Obo,
Eh,
Obo. I think Obo and Abetifi. Her mother is from Obo, and I think her father is from Abetifi.
So, Sarah, did you went for the Easter holidays?
No. This time I didn't go. This year I didn't go.
I didn't know that you are a typical alcohol like that. Anyway, gentlemen, I need to go, so we'll talk. All right. Just WhatsApp me because of any thing that any issue. Just let me know. If you don't understand anything, let me know. We'll talk about that. Okay, guys. Yeah. So I'll see you guys
Okay.
later. Sure.
So we
Yeah.
WhatsApp you.
Yeah, sure. Have a nice weekend.
Okay, so I'm remembering you of the fish farm. So you contacted
Yes,
that.
yes, so that you need to, you WhatsApp me and then let's talk about the fish farming.
Okay, sir. I will do that.
Sure. I'll see you guys later.
Okay, sir. Thank you, sir.
Sure. Bye bye now.
Bye.